Now let's turn our focus to the central limit theorem. We've been talking about the normal distribution, and we've been talking about it based on the entire population. But the one thing we have to know about the population is that it's normally distributed, that it has that bell curve. What if we don't necessarily know that? Well, it may not be practical to look at the entire population. So then we start to focus on the sample means. So instead of looking at the entire population, we're going to look at properly constructed samples. Well, the one thing about the distribution is we're going to look at the same sample size every single time. So if we decide our sample size is going to be, let's say, 20, we're going to look at all the possible scenarios that could occur. So if I have a sample size that's relatively large, there's going to be a lot of possible sets of 20. The sampling error that comes along with this is just simply due to the fact that even if you set up a random distribution and you set it up perfectly, your sample is not necessarily, or in a lot of cases, not going to be perfectly in line with the mean of the population. It's just a good estimate that we have, but there is some error to it, so we have to give a little credence to that. So how do we use it? Well, we're not focusing on just one particular sample. We're going to focus on all the possible samples. If you're talking about replacement, meaning if you start with a sample or a population of 500 and you take 20 out, the next time you go back to your entire population, what ends up happening is the mean of all the samples, not just one sample, the mean of all the samples, so the mean of the means will be equal to the mean of the population. And we talked about standard deviation a few times, and now we have what's called standard error. And what that's simply going to be is your standard deviation from the population divided by the square root of your sample size, which in this case, n represents your sample size. As n increases, what ends up happening is no matter how the population is distributed, whether it's skewed, uniform, normally distributed, the distribution of the sample means does become normal distribution. Since it becomes a normal distribution, we can use all the rules we talked about with the standard normal curve and the applications. The only difference here is our z-score, we have to use a slightly different formula because now we have to focus on the standard error from the means of the samples, not the population, because now we're focusing on samples. Okay? These are the exact same formula. If you notice up here, all it did was a little substitution. If you need to pause the video at this point, go ahead and do that so you can write most of this information down. Okay, let's look at our example. The average number of pounds of sugar that a person living in Sugar Land consumes each year is 218.4 pounds. So that's my mu. We're going to make the assumption here that from previous studies, we're talking about a sample size of 20. So we want to find the probability that a person, one person, selected at random consumes less than 224 pounds per year. Well, because we're only focusing on one person, my sample size is 1, this is actually going to go back to the stuff we've already talked about. So I'm going to find my z-score. I'm going to take my 224, my x. I'm going to subtract 218.4, my mean. And I'm simply going to divide by 25. And I'm going to get a z-score of positive 0.22. And if I go ahead and I draw my normal curve, which is something I always suggest doing, the 0.22 is here. It's slightly beyond the halfway point. So I would expect my answer to be a little bigger than 0.5. I go to my calculator. I use my normal CDF, with this being my upper bound and my lower being an extremely small number. I'm going to end up with a probability of 0.587. So there's a really good chance here that the average person will consume less than 224 pounds a year. But what if we're focusing on a sample now? And we're not focusing on one individual. So there could be one individual who eats a ton of sugar one year, but that person is going to be balanced out by the other individuals who eat somewhere around 218.4 pounds. Still going to find my z-score. My numerator is not going to change. But now I'm going to have to change to my standard error. And my standard error says, take your standard deviation and divide by the square root of your sample size. Well, now think what's going to happen here. Because I'm dividing by the square root of 40, this value on the denominator is going to get smaller. Well, if you use your mathematical logic here, if your denominator gets smaller and your numerator remains the same, your final product is going to grow. So now when I draw my curve, that 1.42 has me out here somewhere. So now I expect to pick up a larger percent of people. If I use my normal CDF, end up with 0.922. So one person, the likelihood of less than 24 pounds, it's reasonably high, 59% we'll say. But if we focus on a sample of 40 people, because of the idea that those 40 people are anchoring each other in, that's going to be practically everybody. So extremely high probability that if I interview 40 people, I'm going to end up at 224 or below. We'll talk about these topics tomorrow. Go ahead and make sure you write all this down and think of any questions that you have, and we can look at them.